Welcome back to the Deep Dive. I know you guys are all about maximizing your knowledge, and today we are really getting into the nitty-gritty of something pretty fascinating.
Yeah.
It's reverse osmosis.
Reverse osmosis. It's a really cool topic. You know, everybody's familiar with osmosis.
Right.
But what about when you flip it around?
Exactly.
What happens then? And that's what we're going to be looking at today.
Exactly. And it's one of those things that we hear about all the time. Like, it's one of those, buzzwords that, like, you see on water filters and stuff. But it's like, how does this actually work?
Yeah.
We're going to look at, like, the core principles of it and why it's such a big deal, especially nowadays. Like, we've got some really cool material for this. So we're going to try to take you from zero to hero on this topic.
Yeah, absolutely. We're going to break it down. We're going to understand the fundamentals.
Yeah.
And we're going to look at, where is it applied? What are the key takeaways? What are the limitations? All that good stuff.
So I guess just starting right from the top, the name itself, reverse osmosis, already kind of implies that we are reversing a natural process.
Exactly.
We know osmosis is about, like, water moving to equalize concentrations across a membrane. What are we flipping here? Like, what's getting reversed?
So in normal osmosis, you have a semi-permeable membrane, and you have a solution on one side that's more concentrated than the other side.
Right.
Naturally, the water wants to flow from that dilute side to the concentrated side to try to equalize the concentrations across that membrane.
Okay.
What's amazing about reverse osmosis is we apply pressure, high pressure, to the concentrated side to force water molecules, essentially against their natural inclination, to go through that membrane, leaving behind all those dissolved solids.
So it's almost like instead of diluting a solution with water, we are squeezing pure water out of a solution. It's like the opposite.
Exactly.
That's really interesting. Okay, so let's talk about these membranes because I feel like that's the real, like, heart of this process. They must be pretty special to, catch these tiny, tiny particles.
Yeah.
How do they actually do it?
Yeah, it's a two-part process. So if we have anything larger than, let's say, a nanometer, it's a very simple case of size exclusion. It physically cannot go through that very dense membrane structure.
Right.
The really cool thing is the way water actually interacts with the membrane itself, allowing it to permeate through, even though the membrane isn't technically porous.
Wow. So it's not like it has, like, literal holes in it. It's more like the water kind of, like, sneaks through at a molecular level.
Yeah, that's a great way to put it. It's almost like a solution diffusion mechanism.
Oh, that's interesting. And in terms of these membranes, are they all made of the same stuff? Like, what are they usually made of?
So you have different types.
Yeah.
Thin film composite membranes are very popular. You'll see things like polyamide being used quite frequently. And then, to kind of maximize the amount of water that can be treated, they come up with all these interesting configurations like spiral wound or hollow fiber to pack as much surface area of the membrane into a smaller volume.
Makes sense. So I guess, like, the more membrane you have, the more water you can filter at once.
Exactly.
Now, we've been talking about this high pressure thing, which is key to reverse osmosis.
Yeah.
How high are we talking? Like, what kind of pressure do we need to make this happen?
It's pretty significant. You're looking at anywhere from, let's say, like 150 to 1,500 pounds per square inch, or, 10 to 100 bar.
Wow. That's intense. And that's all just to, like, overcome that natural osmosis and push the water the other way.
It is. It has to overcome that osmotic pressure. And it also has to, drive a sufficient amount of pure water through that membrane.
So, okay, with that kind of, like, power behind it, where do we actually see reverse osmosis being used? It sounds pretty high tech.
Yeah, if you want ultra pure water, this is the way to go.
Right.
A great example is the pharmaceutical industry. They use something called water for injection, or WFI.
Right.
It's, water that has to be extremely pure for medications.
Right.
What's remarkable about RO is that it can remove virtually all contaminants.
Right.
And so that makes it really suitable for these applications where you need ultra pure water. But it's also used for desalinating seawater.
Oh. Yeah.
In regions where there's water scarcity.
Wow.
Deionizing water for various industrial processes, concentrating valuable small molecules like, some medications, and even in wastewater treatment, it's a really versatile technology.
Wow. So from, like, life-saving drugs to, like, literally making drinking water out of seawater, it's a pretty big deal.
Exactly.
What makes it so good at what it does? Like, what are the advantages?
Well, it's considered the highest resolution separation you can achieve with the membrane process. It's incredibly effective at removing virtually all dissolved solids, giving you that high purity water. Plus, Many RO systems can operate continuously, making them really efficient for ongoing needs.
Got it. But I imagine with that much power, there have to be some drawbacks.
Yeah.
What are some of the limitations of RO?
Sure. So the primary one is really energy consumption.
Right, because of the pressure.
Because of the pressure. You need a lot of energy to generate that high pressure. And the other one is membrane fouling, which is essentially when substances in the water build up on the membrane surface and they start to hinder the performance.
So you have to clean it or replace it.
Yeah, you have to clean it or replace it. And those membranes can be pretty pricey. And, RO is really optimized for separating water from those small dissolved substances,
Right.
not for like really large molecules like protein.
Okay, so not a cure-all, but pretty amazing for what it does.
Exactly.
So I guess to summarize, reverse osmosis is really all about using this high pressure to push water through these super specialized membranes.
Right.
And it can filter out even the tiniest impurities, which makes it ideal for things like making really pure water and taking the salt out of water.
Exactly. It leverages that pressure differential in those specialized membranes to achieve, very high degrees of separation of the water from those small dissolved solids.
This has been a lot to think about. I feel like I have a much better grasp of reverse osmosis now. And given how good it is at removing almost everything from water, it makes me wonder, like, what other unexpected applications or possibilities might there be for RO in the future? Maybe things that we haven't even thought of yet.
Absolutely. Yeah. The potential for this technology is really huge, and it's really only limited by, our imaginations and the development of new types of membranes and processes.
It's pretty exciting stuff. Thanks for joining me on this deep dive.
Thanks for having me. I enjoyed it.
See you next time.
See ya.